We were on chapter number 7, right? And slide was 14th. So this is it. Yeah. So before this, the 13 slides we have gone through this. I'm going back, right? Reverse order, correct? So serial ports is not there. This is what we had done. User mode, privilege mode, copy, run, start, saving from RAM to NVRAM, configuring the host name, banners, and description for the interface, which is not mandatory, of course. Then the console port and telnet port and auxiliary port passwords and enable secret and enable password, and how to disable any command, right? Go on the same mode and just say no host name, no enable secret, right? Whatever. Login, no login. Enable password, no enable password. After enable password, you don't have to write San Jose, whatever. Right, console, exec timeout 00, logging synchronous, interface gigabit 000, whatever. No shut and IP address, right? This was the command to encrypt the other passwords, right? Apart from enable secret, like the console, auxiliary, telnet, and line and enable password. And this is not required. This is the old one. Serial port, we are not doing anything. We are not using serial ports today, right? See, this is the old slide, right? But in the olden days, it was like this. This could be Delhi, right? This could be Chennai, right? And there's a leased line going on. And these are serial ports, right? Whatever ports. They could have a Delhi branch may have one more serial port and one more leased line going to maybe France, right? Paris, whatever, any place. Okay. So this is again one more leased line, right? Going from here, Chennai to maybe Bangalore, right? Whatever. And these were the lands. Okay. So symbolically, this was the olden one, serial port, right? Of course, cloud here, serial ports, electric symbol. But today it will be MPLS VPNs, right? Like this. Of course, will be a cloud there. But these are going to be now gigabit ports, right? Whatever, hopefully. If not 10 gig and 40 gig and 100 gig. Okay, so now we have done IP addressing and subnetting. I hope everybody is comfortable. But just a quick revision, going to the slides. Look at this. Whatever port they are, serial or Ethernet, doesn't make a difference. But this could be India, this could be Australia, whatever, right? And whatever connection it is. So look, both of them are in the same network or subnet, right? 172 is a class B. So 172 to 18, same network. And if it's /24, then third octet is also same, right? Something like this. .1, .2. So hopefully they're in the same network or subnet. Look at this, 172 to 17, opposite ones, 172 to 16, sorry, 172 to 16.01, 172 to 16.02. Both seem to be in the same network, right? Or subnet. We don't know what subnet mask they are using. Look at this, 172 to 17.01, 172 to 17.02. Both seem to be in the same network or subnet. This one is a different network or subnet, class A. This one is a totally different network, class C, right? Okay. Now, one router's different interfaces, they cannot be in the same network or same subnet. Is it okay? Clear? Dipti, Aditya, and everybody else. One router's different interfaces can never be in the same network or subnet. Okay. So this is in a different network or subnet. This one has to be in a different network or subnet. This one has to be in a different network or subnet. Okay. But the opposite ones, they can be in the same network or subnet, because then here intermittently both are in the same network. That means here they are going through layer 2 switches, whatever switches. You get it? They are layer 2 switches, multiple, from maybe India to Australia. But if both the routers are in different networks, maybe India and Sri Lanka, whatever. If they are in different networks, let's say 100 dot blah 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 and 200 dot blah blah blah, that means inside the cloud, it's a layer 3 cloud. Understood? They are going to multiple layer 3 devices. Could be layer 3 switch or a It's basically routing or through routers. Got it? But if both of them are in the same network here, like it was shown in the serial port, 100 dot blah blah blah. Let's say 100.1.1.1, and let's say 100.1.1.2. That means they are going through multiple layer two switches. You can think of a virtual layer two switch, right? A big one, virtual layer two switch. Okay. Therefore, the IPs are in the same network or subnet. Here, this is in 200 dot blah blah blah. That's in 100 dot blah blah. That means they are going through a layer three devices or cloud. Okay. So with this old slide, so all of them are in the same network or subnet. So that means this is a layer two cloud, right? So imagine there's a layer two switch like this, or multiple layer two switches, or a virtual, right? Whatever. Okay, like
Suren, can we
this.
get these PPTs?
Sorry. Yeah, Dipti. One
Can we
second.
get these PPTs to go through?
No, sorry. The PPT is the only thing that I cannot give you because that's the trainer's this thing
Okay.
material. Yeah. So therefore you have the recordings also, and I am also there. Don't worry. After the course finishes, if I am still alive and if you ping me after 6 months, 1 year, and you're talking about the same course, I will definitely help you guys, right? Because we are still on the WhatsApp group. We will remain in the WhatsApp group unless and until you opt to move out away, right?
And we'll have access to the videos, right? Recordings.
Yeah, you can view. Yeah, yeah, you can view the recordings. Talk to the management. I'm also not sure, right?
Sure, sure. Okay.
But as far as I am concerned, anybody can ping me after the course finishes, right? Even after 6 months, 1 year. Okay. Regarding the same course, right? I can help. I will help. Okay, so now if a packet comes on this router for let's say 192.168.1 dot something, if this router doesn't have that entry in its routing table, it will drop the packet, correct? If it has, it will check its routing table. Then it will say go through this X port or go through Y port, or it may point 192.168.1.0 from both the ports. So from X port and Y port, both the ports it can send, right? Either of the two. So if it says router says routing table to for 192.168.1 dot something, go through port X. Then it will receive the packet on this port interface, and it will internally switch the packet on this interface, right? It will keep it on this interface's buffer and then forward it from here to this guy. When it reaches this router above, it will check the routing table, its own routing table. It will look, do I have 192.168.1 dot something entry in my routing table? If not, it will drop it. If yes, hopefully it will say go out from this port. So then again it will internally switch the packet from this interface's buffer to this interface's buffer, and then should be able to forward it from here to this here. And this router it will receive on this port, and hopefully it will check its routing table, and then it will say okay, it's from this port. So internally it will switch the packet, and from here it will send. Only then communication can happen. Okay. So something like this. But if this router said, okay, go out only from this port and not, supposing this is not there, then it will receive on this port and it will forward from this port and it will go like this, right? If both the ports, then maybe one packet from here, one packet from there, one packet from here, one packet from there, load balancing, right? If both the paths are equal, presumably, right? Okay. So unique addressing allows communication between end stations. Path choice is based on destination address, right? So now that's our routing, right? So how we configure it, static routing or default routing or dynamic routing. After this PPTs and all that we have finished switching, we'll jump again into static routing and default routing and dynamic routing, OSPF, right? All those things. Okay, so we know IP, we are talking about version 4 addressing. It's 32 bits and it has got network portion and host portion. And if required, subnet portion also, right? If the subnet mask is non-default. And maximum in the addresses we can go up to 255. So I can have an address like this 1.255.50.25, whatever. I can have an address like this, isn't it? Okay. And then we know 8 bits, right? We know the Bible, right? Every bit has got a place value 1, 2, 4, 8, 16, 32, 64, 128. Where from it has come, we know, right? 2 raised to power 0, 2 raised to power 1, and 2 raised to power 7. So if you convert 255 into binary, it will be all ones, correct? I hope nobody has got doubt in this, isn't it? Dipti and Aditya.
No, sir.
Okay, good. So likewise, we have some IP address, let's say beginning with 172. We know it's class B. Remember the range 1 to 126, class A. 128 to 191, class B. 192 to 223, class C. 224 to 239, class D. And 240 to 255, class E. So we never use D and E. D is used for multicasting, E is used for research and development. So we use only from A and B and C, right? And also 127 we don't use. We know that the PCs use it for loopback, only testing, right? 127.001 something. PC will automatically create for itself, every PC. Okay, so we have some IP address here, 172.16 dot blah 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 dot blah blah blah, 122.204. So we can convert this if required to binary, right? Everybody knows this, how to convert a decimal into binary or a binary back into decimal. Yeah. So nobody should have a problems here. ठीक है, Dipti and Aditya. Yeah.
Yes, sir.
Okay. So now we have class A. The range is 1 to 126. Class B, 128 to 191. Class C, 192 to 223. And class A, first octet goes in the network portion and the rest three go in the host portion. Network is always on, right? So the subnet mask for class A will always be 255 dot, host is always 0, 0 dot 0 dot 0. Yeah. Likewise, class B, two octets go in the network portion and two octets go in the host portion. So this will always be 255.255. And if it's a default subnet mask, then it will be 0.0. Again, class C, three octets go in the network portion. So 255, the subnet mask, 255.255 will always be there. And if this is a 0, that means it's a default subnet mask, which means one network, no subnet, correct? And likewise, we have class D. So from 224 to 239. This is used for multicasting, right? So if you take any class A IP address 1 to 126, if you convert it any into binary, first bit will always become a 0, right? Whether 126 or whatever, correct? First bit will always be a 0. Likewise for class B, the first two bits will always be 1, 0, correct? First two bits will always be 1, 0. And likewise, class C, first three bits will be always be 110. They are reserved fixed. So don't worry, we don't have to do anything. Likewise, class D, 1110. So 0, 10, 110, 1110. Okay. Okay. Now we have a router with two interfaces, Ethernet 0, Ethernet 1, whatever. And they have given some IP address here, 10.6.24.2, and they have given some address here, 116.2.1, right? And obviously we have switch here and it is connected to many more devices. We have maybe a layer 2 switch like this. Okay. So then look, what subnet mask have they given here on the interface? If you go on this out and give a command show IP route, it will tell you like this, connected, connected. Of course, in the olden days, we didn't have that local and local exact interface IP address. It was only CNC. So here, somebody must have given, it says 10,000. So must have given 255.0.0.0. That means default, right? So you can give from 10 anything now here, right? To 10 2 raised to power 24 minus 2. More than 16 lakh addresses you can give. Too many. Okay. And here, how do you know? Because they have given 255. That means /8, which is 255.0.0. That means 8 bits are on in the subnet mask. Right. So what it does is it does Boolean ANDing 10 and 255. Where you have 255, Wherever you have 255 the subnet mask, that number will filter down as it is, right? So had somebody given here /16, that means 255.255.0.0, then here it would have been 10.6.0.0. Understood? Had somebody given /24 there, here, which means 255.255.255.0, then this would have been 10.6.24.0. You get it? Likewise here, somebody must have given /16, the default subnet mask. So it's showing here 172.16.0.0, right? Only the first two numbers. समझ में आ गया? Understood, guys? Dipti, Aditya. So this is class B, this is class A. Here you can give 2 raised to power 16 minus 2 maximum. 65,536, that's equal to 65,534 addresses you can give. So keep giving, right? It says the first two numbers are in the network portion and the third and fourth octet are in the host portion because that's a default subnet mask, right? /16, which means 255.255.0.0. Okay. Had somebody given here 25550, then here it would have been 172.16.2.0. Understood? Something like this. So it will do Boolean ANDing. The router takes the interface IP address and subnet mask and does Boolean ANDing and says, okay, this pillow or this child belongs to this network, right? Likewise. ठीक है?
Yes.
Okay. So now, without subnets, which means what? You only have layer 2 switches in between, right? A LAN like this. So they have taken a class B, and that means they have taken /16 default subnet mask, right? No subnets. 255.255.0.0. So if we know 2 raised to power 16 minus 2, 65,536 minus 2, these many addresses you can give. And what will happen? 172.16.0.0 you can't use network IP address. 172.16.255.255 you can't use being the broadcast IP address. Got it? So what will be the first one? 172.16.0.1, right? What will be the last one? 172.16.255.1 less than this one. 254. Total will be how many? 65,534. 172.16.0.1, 172.16.0.2, 172.16.0.3, right? You keep going like this. 172.16.0.3, 172.16.0.4 till 172.16.0.254. Can you give 0.255? Can you give 172.16.0.255? Yes or no? Deepti, Aditya? Hello, hello. See, what you cannot give is given below. 172.16 here. 172.16.255.255 you cannot give.
We can give.
Yeah, you can give. So next, 172.16.1.0. Likewise, 172.16.1.1. Keep going like this. 1.2, 172.16, 1.3 till 1.255. Then next will be 172.16, 2.0, 2.1, 2.2. Keep going like this till 2.255. Got it? Likewise, you will go up to 116, 255.255. Only then you will get 65,534 IP addresses. Okay, big network without subnets. So if you take to give here this one, then here you have to give a different network or subnet. Different network, not subnet, because this whole network is gone here. So you can take any other network or subnet, any other network subnet here, right? Or a different network there. Okay. Now look with subnets. So what they have done? They have taken this, which means 255.255.0, big network. Now they have broken this into multiple subnets. They are not using this. That means they are subnetting. So let's say I take /24. So I borrowed 8 bits, 2 raised to power 8. So now I will have 256 subnets. Got it? How many? 256 subnets. And in every subnet, 2 raised to power 8 minus 2. 2 raised to power 8 minus 2. 254 addresses per subnet. Right? 254 addresses per subnet. Got it? So 255.255.255.0, correct? That's /24. So interesting octet is third octet. Delta is 256 gilli gilli minus 255, 1. So change will be in the third octet with 1. What will be the first subnet? 172.16. I don't have to write. It's common for all. Dot 0 dot 0 /24. What about the second one? 172.16.1.0 /24. What about the third one? 172.16.2.0 /24. Next one, 172.16.3.0 /24. Got it? Likewise, 172.16.255.0 /24. Got it? So you take any subnet, let's say the first one. Broadcast will be 0.255. Right? You can't use this subnet IP address. 172.16 0.1, 0.254. You can't use this broadcast. Right? So you can do Boolean ANDing, you can do delta, right? This way. So look what they have done. Here, this interface, and here switches here. So they have taken from this subnet, 172.16, next one. They have taken this subnet, this one, 1.0. So 1.12, 1.254 they have taken. 1.255 you can't use. 1.0 you can't use, right? Taken this subnet. So you give here 1.1, 172.16, 1.1, 1.2, 1.3, 1. Up to 1.254. Likewise, you go there and give 172.16, 2.1, 2.2, 2.3, 2.4, likewise, up to 2.254. Likewise, here you can give 172.16, 3.1, 3.2, 3.4, 3.5, right, up to 3.254. And here you can give anyone 172.16, 4.1 up to 4.254. So you can give any two numbers from that range. 1.172.16, 4.1, 4.2 would have been okay. Or 172.16, 4.1 and 4.254. Or 172.16, 4.100, 4.200, anything. Okay. Only a demo here. समझ में आ रहा है ना दीप्ति आदित्य
Yes, sir.
दीप्ति when I speak in Hindi समझ में आ रहा है ना you understand that or not
I know Hindi, sir.
good wonderful sorry I keep on forgetting and again ask sometimes okay good Aditya I know he has got no problem so wonderful ठीक है समझ में आ गया हाँ आदित्य okay with this
Yes, sir.
so they have not used the first one see 0.1 0.2 0.3 because this is a very old slide right in the olden days on the router there used to be a command no IP subnet 0 -0, which means what? This first subnet, Cisco used to say, don't use this first subnet, 0 subnet, and this one, the broadcast subnet, or the first subnet and the last subnet. Got it? But now it is not no. Now the command that comes on automatically from the factory is IP subnet 0, which means what? You can use the first subnet and the last subnet, or the first subnet, right? Or the subnet 0 and the broadcast subnet. You got it? So instead of you can use now 0.1, 0.2 also. Okay? If anything you don't understand, you have to interrupt me and say, I am not able to understand. Okay? Because when you don't speak up, I'll presume that yes, you have understood and I will go ahead in the interest of time. So now here, look. So IP root 116, 2.0, 3.0. So they have used subnets, right? 2.0 and 3.0. So 2.1, 2.2, 2. up to 254 you can give. Right here, from 3.1 to 3.254 you can give. Okay. But you cannot have same addresses in a LAN on two devices. Maybe routers interface the same 3.5 and PC also same. No, you can't have. You can't have same addresses in the LAN. One given to the router interface and one more given to the trying to give the host. It won't take only. Okay. That's not possible. So now it's subnetted /24, right? All of them. So it says 176 in first two octet gone network, third octet gone in the subnet, and the last one in the host. Okay. Now we know what is subnet mask. Subnet masks begin with 255. It bifurcates the network portion and the host portion. Right? It tells you how many bits are in the network portion, if required in the subnet portion, and then how many bits in the host portion also. Right? So we have a class B address here, 116.0.0, and we have a default subnet mask, which means what? One network, no subnet. So first two octets definitely as a law rule, they go in the network portion, fixed, lock kiya jaye. And host portion is 16 bits, right? Also known as /16. Subnet mask, prefix mask. Prefix. First 16 bits are fixed in the subnet mask, right? Okay. Now we have the same IP address, but if we change the mask, we take a new one. Let's say 255.255.255.0. So we can also say now /24. Now this is not default. So it's subnetted, right? So we have 16 bits in the network portion, 8 bits in the subnet portion, and 8 bits in the host portion. 2 raised to power 8. So we have broken one big network into smaller, 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 256 subnets. 2 raised to power 8, right? And in every subnet we have 2 raised to power 8 minus 2. 254 usable host IP addresses. Is that okay? We know this Bible now, where it has come from. And all zeros means decimal 0. Or decimal 128 means what? 1 bit on and from left to right normally, right? Highest to lower order. 7 bits zeros, 7 zeros. 192 means what? So if 2 bits are on, right from left to right means what? Add 122, 128 plus 64 above, right? That's how much? 192. I hope we know all these things, right? First 3 bits are on from left to right means add 128 plus 64 plus 32, that's 224. 4 on, 4 off. Britannia, Delight, ding, 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 240. That means 128 plus 64, 192 plus 32, 224 plus 16, 240. Right? And 5 bits on, 248. Right? This one also. 6 bits on, this one also, 252. 7 bits on, this one also, 254. And all the 8 bits on, 255. Right? Okay. So now we have some IP address and some subnet mask. So now this seems to be a class B and a default subnet mask. So obviously you can do the Boolean ANDing and find out. You will come to the conclusion that 172.16, 2 octets got in the network portion. 0.0 will be the network IP address. And 172.16.255.255 will be the broadcast IP address, which you can't use. First will be 172.16.0.1. Last will be 172.255.254. One less here, one less here, one more there. Fourth octet only. Correct?
Yes, sir.
So then this IP address will belong to this network IP address. And you can now find out the first visible, last visible, and the broadcast IP address. Okay. Because the default subnet mask, that means subnets not in use, only one network. But now, same IP address, but if we change the subnet mask, which means what? This is not the default. So then you got to find out this child or Pillu belongs to which subnet IP address, and the first and the last and the broadcast. Now we can do it in 2 methods, Boolean ANDing or delta. That's a shortcut method, right? Shortcut. Okay. Delta method in the book is also known as block size method, right? Block size method. Okay. Same thing. I hope everybody's clear on this, right, Dipti and Aditya? We know how to do all these things, right? We have done it long back.
Yes, sir.
Okay, fine. So you take this IP address and do Boolean ANDing. You'll find out that this guy belongs to this subnet, right? And then you can find out the first and the last and the broadcast. Okay. You can do it with the delta method or Boolean ANDing, whichever. Again, some IP address, but a different, just an example, subnet mask. So again, you can do Boolean ANDing or find out interesting octet, this one. What's the value of delta? 256 minus this 192 is how much? 64. Divide hypers by delta. Remember, hypers is how much? 160. Divided by how much? Delta is 64. 64 how many times? 6 2s are 12, 6 is 18. Okay, 2. 64 into 2 is 128. That's it. Multiple. That's your subnet hypers. See that? First will be what? You can't use this subnet hypers. Network or subnet, one and the same thing, right? And then you can find out the first, which will be 1, so 16, 2 dot 129. This plus delta minus 1 is my broadcast. Delta is 64. So 128 plus 64 is how much? Minus 1. 191 is my broadcast. Got it? You can't use this. You can't use this. First is 129. Last is 190. Total is how much? 2 raised to power. How much is delta, man? 64. 2 raised to power 2, 4, 8, 16, 30, 64. Minus 2. 62 hypothesis. Yeah. Are they 62? Yeah. Including both. Yes, they are 62. Correct? So now we know which addresses you can use, which you cannot. So we go under that port, whatever it is, gigabit, and we say no shut to enable the port, and then you give whatever address you want to give. So you can't give your 1.0 or 1.255 because it won't take. You know why, right? And you can also give a secondary IP address, right? Supposing if I use this, then I can use some 10.1.1.1 to 10.1.1.254. But boss had said 5 years ago, we are only 50 guys. In 5 years, we have now how many guys? 254 guys. And now 10 more guys shall be joining next week. Where do I place them? So I can take one more subnet. And from that subnet, I can give some IP address and say secondary. So now the other guys, 10 guys, they will have 10.2.2.2, 10.2.2.3, right? Like this, up to whatever in that subnet. Okay. This is also possible. Show interfaces up and up, very good. That means that I can come and go. And this is a router. So this Ethernet port has got this MAC address. Of course, we don't have to do anything with this, but we know this IP address we have given to this guy, right? This subnet mask. And the rest, other things are coming by default from the factory only, right? So I think we have gone through this, but MTU is always by default maximum transmissible unit. That means the packet size will be by default 1500 bytes, right? That much of data can come and go through the interface, right? And bandwidth is always in kilobits per second. This is an old slide. It's a 10 Mbps one, right? Delay, whatever it is in USEC, all this 1000 is coming from the factory default settings, right? We don't have to play or do anything. Relay, again, some value, 255/255, right? Reliability and load, 1/255. So all these settings are from the factory only. We can change it. We don't have to in this course, right? Encapsulation, Cisco calls Ethernet as ARPA only. We don't have to do anything. Loop back, not set, keep alive at 10 seconds. Okay, every 10 seconds, it must be sending a signal. Hello, like pulse, right? So it should receive also back. So if the other guy is sending, then only I'll receive. Otherwise, okay. And rest, other things we are not concerned with. Last input, okay, on this interface, Ethernet 0. 7 seconds again, I received some signal or data, whatever. And output was 8 seconds ago. Okay. So anyway, we don't have to do with this. Last ring of show interface, I don't care. Queuing strategy is first in, first out. So whichever packet comes first on the interface, right, in the buffer, I can queue them up to some limit, right? The first packet I received, I'll that forward that packet first from interface, then the second one, then the third one, right? Like this. LIFO means last in, first out, right? LIFO. Anyway, we don't have to do anything with all these things. Output queue, output queue. That means, let's say this is Ethernet 0. So if I receive packet from some other port and it needs to be output, right, sent out from this port, then on this interface's buffer, I can hold up to 40 packets, right, in the memory. And right now I am not holding any packet. And likewise, input queue. Input queue means like coming from the switch LAN towards on this port. So I can hold up to 75 packets, but right now I'm not holding anything. Okay. 5-minute input rate, 5-minute output rate, blah, blah. Nothing there. Okay, so far we have received these many packets and there were these many bytes on those packets, blah, blah. Received so many broadcasts. I have told you about runs and giants, right? Have I told you about runs and giants before? Throttles, ignore, we don't have it in the book also. Runs and giants, remember? Or if you want me, I can repeat that. Yes, Aditya and Dipti.
We haven't done it, sir.
We haven't. Okay, very good. We haven't. Wonderful. So look at this giants. What is giants? So let's say this is a old scenario. We have a donkey hub here, right? First, let me explain you runs, right? I'm trying to explain now runs first. Okay. What's runs? So if two devices send at the same time, is old story hub, and they would collide. So if the packet would come up to this point, it would be definitely less than 46 bytes anyway. And the router would by default drop it. We don't have to do anything with all these things, right? Okay, so how many packets I have received so far, which are less than 46 bytes? So if I receive one packet, this run counter will go to 1. If I receive one more packet, run counter will go to 2. Got it? But today it may not happen. Understood runs? This was in the olden days, right? When you used to have this donkey hub connected. And if two devices sent at the same time, the packets would collide and it would go to this interface and it would definitely be less than 46 bytes because of the collision. And the router will definitely drop it. We don't have to do anything, but the counter will keep going up. What about giants, right? Now giants, so runs understood. Now what about giants? This is your, so user mode enable, privilege mode configure terminal, interface, blah, 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 right? Let's say gigabit user interface, right? Now, here if you put a question mark, so the command will be either IPMTU or directly MTU, right? Either of the two. And if you put a question mark, maximum transmission units, how much is default MTU? 1500 bytes, right? Now let's say if I go there and make it 900, of course we are not going to do it, just an example. And now if the packets which come, if they are more than 900 bytes, right? You get it? If they are more than 900 bytes, and again inside that packet, there's a fragmentation thing. It will be either 0 or 1, right? So you don't have to go into that detail, but either it will drop it or it will, if it's more tan 900, let's say if it was 1000, what it will do is it will break it 900 and 100 and then send it, or it will drop it depending on such values. But you get the meaning of giants, right? Runs and giants. Default was 1500. But if I just go there and maybe, right, make it 900, and if then packets which are less than 900 but more than 46 bytes, it will definitely forward it. But if they come more than 900 bytes, then it will, depending on what's the value in that packet for fragmentation bit, either it will drop that packet or it will break it and send it, forward it, right? So this was your runs and giants. Well, nobody will explain you all these things in the class, right? It's not possible. Okay. Likewise, you have to keep an eye on all these errors, right? Mostly all these errors will be hardware problems, right? Hardware issues not to be covered in my course, or it can be speed or duplex mismatch. Duplex mismatch. Have I explained this before? Duplex and speed mismatches before, Aditya and Dipti? Have I explained this before? Speed and duplex mismatch. Very old laptop, 30, 40-year-old from the museum. If you attach to a switch port. Have I explained this before?
No, sir.
No? Okay. Very good. So look, collisions, right? Mostly it will be hardware issue. Not to be discussed in my course. Not covered at all in my course. Okay, otherwise, speed and duplex mismatch. Mismatch. Sometimes if I explain again, after that you may realize that, oh yeah, I think the trainer had explained all the things before also. Anyway, don't worry. So supposing I am taking the example of switch and the, maybe it's a multi-layer switch, right? Whatever, and the PC. This is a very old PC, 30 years old, right? It's lying in the museum, right? Nobody uses it. But its LAN card those days supported only and only half duplex, right? And supported only and only 10 Mbps speed. Very, very old PC, desktop, right? Whatever. And this switch is, let's say, a gigabit port, if not a fast Ethernet port. Okay. So the moment you connect this PC to this switch port, the switch negotiates with this PC. Hello, hey, you PC, what speed do you support? The PC says, man, I am an old PC, very, very old PC. My LAN card supports only 10 Mbps. This guy from 1000 Mbps or 100 Mbps, whatever it is, will come down to automatically 10 Mbps because speed and duplex are in auto mode, right? So they automatically negotiate with the device connected on that port, right? So, very good. Now both can work only at 10 Mbps, send and receive, okay? Okay, also after what the PC switch is going to ask the PC, what about your duplex settings? It says, man, I support only and only half duplex. Okay, so this will automatically go to half duplex. And now the PC can only send or only receive one thing at a time, right? But if, supposing if I go on the switch and say user mode enable, privilege mode, configure terminal, global mode, interface, gigabit 0/1 port, whatever this port is, right? Let's say come under the interface mode. And if I say speed, mine was already 1000. So if I make it 100 Mbps or if I deliberately make it 1000, so what will happen? This is a speed mismatch. Got it? This is a speed mismatch. This works on 10 and you said 1000 there, if not 100. Communication will happen, but it will be slow and a lot of collisions will happen now. Okay. So it will be slow down. It will slow down the communication. Secondly, this was speed. Now duplex. Supposing if I go under this port and also give a command, duplex question mark. When I give speed question mark, it gives me three choice, 10 Mbps, 100 Mbps, and supposing it was supporting gigabit also, right? So like this, three choices. For duplex, if I give a question mark, it will give you auto choice, half duplex, and full duplex, right? Three choice. So by default, it's an auto. So if I don't play with it, it will ask, hello, what is your duplex setting half? So he will also come on half duplex automatically. Very good. But now if I go there and say duplex full, What's happening now? This is a duplex mismatch. Got it? This works only on half. That is now somebody, some idiot DJ has gone there and given a command duplex full. So this is known as duplex mismatch. Understood? This must not happen, right? Communication will happen, but it will be slow and these collision counters will go up. See all those things nobody will explain in the class, right? There's no time to get into all this such detail. Not possible. Understood? Runs, giants, collisions, late collisions, right? Mostly it will be a hardware issue. Cable problem, connector problem, whatever, right? Not my course. Okay. Now the port must be up and up, any port. Show IP interface brief or show interfaces, whatever. It should be up and up. Only then from that port communication can happen, right? So the first up before this comma is physical layer. And the second up after this comma is data link layer. So if it is up and down, no good. Communication cannot happen. Down and down, no good. Communication cannot happen. And administratively down and down, also no good. Communication cannot happen. Right? Carrier means cable detect. Keepers means signaling, right? Protocol. Okay. So up and up, they technically call it operational. Very good. Nothing to worry. Right? Data can be sent and received. Connection problem means up and down. Interface problem means down and down. Disabled means, of course, all the ports from the factory, they come disabled on the router. You got to go on the port and give a command, no shut, right? Because otherwise it will show you administrator down and down in show IP interface brief command. Remember that? We can see that again, show IP interface brief command. Now, after we finish all these things, when we get into routing, we'll be giving this command every day, right? N number of times during a couple of days, right? So up and down, it says connection problem. Down and down, it says interface problem. Okay, even after 22 years, I don't remember this. But up and up is very easy, operational. Disabled is also very easy, administrative down and down. Then to make myself realize, though it's not very important, I imagine that I take a screwdriver and break this port only. So this has gone down. So it will be down and down. What did I break with the screwdriver? I broke the interface. So interface problem is what? Down and down. Okay. This silly thing this story I created for myself to remember. Up and down is what? Connection problem. Now up and down means maybe I have not connected. I have said no shut, but I have not connected the cable only here. Right? So it may be up and down. Or the cable is connected, but the other end is lying on the floor. So up and down. Or it's connected to a device, but this device is powered down, not powered up, right? So it may be up and down. Or this device is powered up, but this port is still shut down, right? So it may be up and down. Okay. So connection problems. And screwdriver means I broke the interface. So interface problem is down and down. So if physical layer is down, data link layer cannot come up. Right? Physical layer is up, data link layer may be down because signaling problems. Okay. We don't have serial ports today. Nobody in the world uses it, right? Uses this one. So, but if you can go and change the bandwidth also, go under the interface and you can give a bandwidth command. Of course, we are not going to do it. Bandwidth, you can change it, right? Ours was gigabit is 1000 Mbps, 100 Mbps or 10 Mbps, right? Whatever. You can change it. Anyway, rest all okay. Serial port gone. We are not concerned with serial ports. Okay. From the privilege mode, you can get to the global mode by giving commands, right? Privilege mode, say configure terminal and you come to the global mode. Giving you access to specific router configuration modes. From the global mode, you can go to line mode, controller mode, router mode, interface mode, sub-interface mode, blah, blah, right? Using the CLI, you will configure the router's name. You know how to give the host name. You know how to give all the passwords and other console commands. Line console 0, logging synchronous, no exit timeout. A router's main function is what? Is to relay packets, is to forward packets from one network device to another. So you must define the characteristics of the interfaces through which the packets are received and sent. In other words, just go on the router's interface and say no shut and then give an IP address. That's it. Okay. In a TCP/IP environment, end stations communicate seamlessly with servers or other end stations. This communication occurs because each node using the TCP/IP protocol suite has a unique 32-bit logical IP address. Got it? By dividing a network into smaller segments or subnets, you can make the network address use more efficient. There is no change in how the outside world sees the network, but within the organization, there is additional structure. Okay, I'll theory man. Understood subnetting? A subnet address is created by borrowing bits from the host field and designating them as the subnet field. Is this understood? 10.1.1.1, 255.0.0.0. Only one network, no subnets. But if you want to break it, so in the host portion now there are 24 bits. Network portion, of course, there are 8 bits. If you want to make it subnetted, then maybe I'll make it /16. So from this 24 bits, I convert, let's say, 8 bits into ones. And now only 16 bits are remaining in the host portion. So if you want to create subnets, from where do you borrow bits? Network portion or host portion? Network you can't because they are fixed, 8 bits. There were 24, you borrowed some bits, maybe 1 or 2. In this case, we have borrowed 8 bits. So now in the host portion from 24 bits, we are only left with 16 bits. So we have subnetted that. ठीक है ना? समझ में आ गया दीप्ति आदित्य?
Yes, sir.
So the number of borrowed bits is variable and specified by the subnet mask. In class C, you have 24 bits from which you can borrow. Class B, you have only 16 bits from which you can borrow. Class A, sorry, I'm telling the other way around. Class A, we have 24 bits from which you can borrow bits and to convert them into subnets. Class B, we have 16 bits, and class C, we have only 8 bits from which you can borrow some bits and convert them into subnets. Okay. Each interface on a Cisco router must have its own address to uniquely identify on the network. I told you this. One router's 2 interfaces can never be in the same network or same subnet. They have to be in different networks, or they have to be in different subnets. ठीक है? When you complete the router interface configuration, you can verify it using show commands. Show run, show start, show IP interface brief, show interfaces, show interface, blah, blah, blah. Gigabit 0/0/0, whatever. Okay, so we get into this one. What is this? Okay, this also we have done. CDP, LLDP.
Yes, sir, we have done.
Yeah, we have done this, right? So nothing to worry here. And router components we have done. Booting up sequence and, right, router components. याद है? We have done it, na? RAM, ROM, and RAM.
Yes, sir, we have done it.
CPU, yeah. And that configurations values and all those things, right? And now we begin with managing Cisco devices. What is this? Okay, we have done this also. We know how to take a backup on the TFTP server. Yeah, correct?
Yes, yes, sir.
So we have done this. Okay. What more? Now we begin with switching, right? PPTs. We have completed switching, VLANs, everything. But now let me run through this switching PPT. So now upon completing this module, we will be able to explain how bridging and switching operates. Whenever you read bridging in the books, presume it is switching only, right? Explain the purpose and operation of a spanning tree protocol. We know what it does, loop avoidance, right? Avoids loops, right? Election of root bridge and election of root port and election of designated ports and all other ports block. Lower priority, lower MAC address. Remember all these things, yeah?
Yes, sir.
So verify the default configuration of the device. Now we are talking about switching only. Given a functioning access layer switch. So all the ports on a switch are enabled by default, right? Unlike a router where all the ports are disabled by default. Because this is a LAN device, right? I'm talking about layer 2 switch. And IP address is 0.0.0.0. There are no passwords. All the ports belong to VLAN 1. This is all the default settings. Got it? VLAN 1, VLAN 1002, 1003, 1004, 1005. They're all there by default only. You can create more VLANs. Build a functioning access layer switch configuration to support the specified network operational parameters given network design. Now you can create VLANs, you can assign ports to VLANs, right? All those things. You can configure port security, Ether channels, whatnot. So execute an add, move, or change on an access layer switch given a new network requirement. Okay, all theory. Okay, so now we know what a switch does. It can take forwarding and filtering decisions, right? Filtering means dropping. It can automatically, that means dynamically, learn the MAC addresses, right? And it can avoid loops automatically, right? Avoid loops. That's the job of STP or RSTP or PBST or MST, whatever. And also unknown unicast.
Unicast, multicast, and broadcast.
Yeah. Unknown unicast, it will flood. Multicast also it will flood. And broadcast also it will. We know these 6 things, right? Very sure. Now, upon completing this lesson, we'll be able to describe layer 2 switching and bridging operations and modes, describe how LAN switches use and populate the MAC address table. Okay, fine. So here we have a small topology. This is a very old slide. So presume we have a donkey hub connected to this switch here. And like this. This is a donkey hub. We have one more donkey hub here. And presume like this. So now any switch can automatically learn the MAC address, take forwarding and filtering and avoid loops. Okay. Now tell me, looking at this diagram, assuming I have shown you the hubs there, how many collision domains are there and how many broadcast domains are there? Yeah. How many collision domains are there and how many broadcast domains are there? How many broadcast domains?
Is it 3?
3. Okay. Dipti, uh, because we don't know anything, we are presuming that all the switch ports are in VLAN 1, correct? By default. So if one sends a broadcast, it will go to everybody else, correct? I
Right.
received this here, I'm in VLAN 1. So I will send out from all ports which are in VLAN 1. All my ports are in VLAN 1. So it will go to everybody. So that means there's only one broadcast domain, correct?
Okay, sir, got it.
Simple, right? Good. Now what about collision domains? How many collision domains? So this is hub, old donkey hub. Of course, nobody in the world will use today a hub. But we say every port on a switch is a single collision domain, right? So one collision domain, another collision domain, 2, 3, 4. This is one 5. This is one 6, 7, 8. And this is 9. And this is 10. That's it. Okay?
Then
Understood? 10. But if you say there's no hub there and they're directly connected on switch ports, then obviously 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? collision domains. ठीक है? Now, whenever a frame comes on a switch port, it can forward it in three ways. One is cut through, one is store and forward, and the third is fragment free. Which method your switch follows, that depends on the hardware platform and iOS versions, right? Different switches may have different methods of forwarding it. But yours will be, I think, today, store and forward method. In the olden days, when we had 1900 switch, that by default it was cut through, right? Anyway. So what happens in cut through? Switch checks the destination MAC address, obviously, and immediately begins forwarding the frame. Okay. Which means what? Even if there's error, it will forward. No error or no error, it will forward, right? It's going to check only the first 46 bytes, right? Whether error or no error, it will forward or flood, whatever, right? What happens in store and forward? Complete frame is received and checked before forwarding. So normally data will be 1500 bytes. So it will come on this, allow the frame to come on this port. It will do all checking. If there's error, it will drop it. If there's no error, it will forward it. Okay. Fine. 900 series of switch, but data is around, let's say by default, 1500 bytes. Okay. So whenever a switch receives a data or frame on a switch port, it's a layer 2 switch, presumably, right? So it checks the destination MAC address, obviously address means MAC address, and immediately begins forwarding it. Okay. So it is going to check only the first 46 bytes, right? Whether error or no error, it will forward it. Okay. Store and forward. Let's say it has received this frame. Earlier also it checked 46 bytes, but the frame size was 1500 bytes. But it checks only 46 bytes of the 1500 bytes, right? And then forwarded it. Now it is going to complete frame resistant check. It's going to check all the 1500 bytes. If there's error, it will drop it. If there's no error, it will forward it. Okay. Now fragment tree is a compromise between cut through and store and forward. Now tell me latency, which will take more time and which will take less time between cut through and store and forward. Where is the latency more and where's the latency less? Latency means the moment it enters one port and the time it takes to forward from another other port, that number of milliseconds or microseconds for which the frame is inside the switch before forwarding it out. That time is known as latency, isn't it? Now, cut through latency is less or more? Or store and forward the latency is less or more? Which one is going to take less time? Cut through or store and forward?
Store and forward, because cut through only 46 bytes out of 1500 bytes.
It's going to check that and forward it. Isn't it? In cut through, the switch is going to check how many bytes
46.
of the
1500.
and store and forward is going to check how many bytes.
All the 1500.
Correct. So which one is going to take more time?
Store and forward.
Correct. So latency is less in cut through and more in store and forward, isn't it? Correct?
Yes, sir.
And store and a fragment free is a compromise between the two. Right? It takes more time than cut through, but less time than store and forward, because it's going to check the first 64 bytes, which means it will take more time than cut through, but it will take less time than store and forward. Correct? And if there's error, obviously it will drop it, and if there's no error, it will forward it. Okay. The switch checks the first 64 bytes and immediately begins forwarding it. Now, initially the MAC address table is empty. We know that the switches maintain MAC address table. So you connect 4 PCs, port number 1, 2, 3, 4, MAC address 1, 2, 3, 4, whatever. Yeah. So initially the MAC address table is empty. So how does it learn? When does it learn? Now let's say A is sending data to C. So let's say this is 10.1.1.1. Let's say this is 10.1.1.2. Let's say this is 10.1.1.3, and this is 10.1.1.4. A is pinging, let's say C is pinging 10.1.3. What will happen? That will come inside this port. Source MAC address will be this, source IP will be this, distance IP will be this, distance MAC will be this. When it comes inside a port, it's going to check the incoming frame source MAC address. If it is not there, it will automatically cache it, right? E0, because I received this on E0, and the source MAC address is 1111. Now it will look at the destination address 222. It doesn't know. What will it do? It will flood it from every other port. It will make Xerox copies and give to everybody else, because I don't know where is 222. Got it?
Yes.
So when it is forwarded to this guy, communication is over. But the still doesn't know where B 222 exists, right? This one. Okay.
Yep.
Which caches the MAC address of A to port E0 by learning the source MAC address of the incoming frame, right? Frame A to C is flooded out all other ports except the incoming port, because the funda is unknown unicasts are flooded. Simple. Now D sends a frame to C. So 10.1.4 is going to ping 10.1.3. What will happen? Source MAC will be this, destination MAC will be this, source address will be this, destination will be this. It's going to come on this port 3. Incoming frame 4. If the entry was not there, it will automatically make an entry. Cache an entry means it will automatically make an entry in its MAC receiver, right? And then it doesn't know where 2 is. So it will flood it from except the incoming port, it will send it to everybody else. Correct? Because unknown unicasts are flooded. Hmm?
Got it, sir.
Switch caches the MAC address of D to port E3 by learning the source MAC address of the incoming frame. Now there will be a time when it knows all the MAC addresses, all the 4. So then A is going to ping, let's say C. That means data is going to come on this port. It's going to look at the incoming frames 1. Okay, the entry is already there, nothing to do, nothing to worry, right? And it's going to look at the destination 222. Okay, I know that also. So I got to just forward from my E2 port. So it will receive on E0 port and forward from here, and not forward from any other port. So it has taken a forwarding decision on port number E2 and filtering decisions on all these ports. That means it's going to drop on all these ports, not forward it, right? So we know forwarding and filtering decisions, right? How it takes. This is known, therefore the frame is not flooded. Okay? It will only forward from E2 port. That's it. And this is a very, very old story. Now we don't use a hub here. In case 30 years back, 40 years back, whatever, 20 years back, we had a topology like this. In case we had a topology like this. On one port of this hub, idiot donkey, we connected this PC and another port. We connected this PC and another port. We connected a switch. Now, if A sends to B, what will happen? It will come on this port. This donkey only knows one thing. If I receive on one port, I just got to make Xerox copies and send it to everybody else on other ports. That's it. So this guy got it. But one frame came on the switch port also here. Switch is going to look at the source MAC address 1111. It knows, okay, it has got entries here, right? It knows 1 also and 4 also, both from E0. What will the switch do now? What will it do? It has received a frame on E0. It knows source is 1111 and destination is 4444. It's going to check its MAC address. Both are from E0. What will the switch do, Dipti? Can you give me some idea, hint? What do you think the switch will do?
I'll send the frames because I'll send the packets.
It will forward the frame
Ah,
from E0 port.
correct.
It won't actually. Okay.
Why is it, sir?
Because when the source and destination both are on the same port, right? It will
Filter. Okay.
this younger brother is a donkey, brainless. This elder brother has got brain, right? What if this elder brother also behaved like a donkey? And as per our belief, even I had thought initially when I was new to this, I thought it will forward from this port only. But one thing, whenever it receives a frame or data on one port, from the same port, normally they don't forward it. Got it?
Okay.
Now let's ask, okay, assuming that you are in my initial logic, what we said very confidently, it will forward from E0 only. Fine. I also thought the same way. Let's for a moment think, okay, it received from here and it forwarded again back from E0 only because both are on that port only. So this donkey hub will receive on this port. What will it do? It will send one copy to this guy and send one more Xerox copy to this guy, correct? In that case, correct? Isn't it?
Correct.
So this guy will say, man, I sent something, it has come back to me, boomerang. Correct? So this is a
Right.
loop. And this guy said, I had received one copy earlier, and now I am receiving one more copy of the same thing. What nonsense. Multiple packets, right? Multiple copies of the same frame. Nobody likes it. Unrecoverable damages, right? It's like I coming and telling you, hi Dipti, tomorrow also. And I'll take up this same chapter which we did yesterday. What will you say? Right?
Right.
You will say, hey, DJ, we had done this whole PPT yesterday, man. We spent 1 hour on that, 2 hours. You're taking the same chapter again? What nonsense. Same topic, you wouldn't like to receive. Same multiple copies, got it? Of the same packet. Nobody likes it. We finished the chapter, go ahead, isn't it? So VLAN I explained yesterday. Again today I come and say, okay, Dipti, I'll explain you VLAN again. You'll say, what nonsense, man. I understood yesterday you explained VLAN. Let's take some other topic today. No, let me explain VLAN only. So multiple frames, right? You'll just perhaps close your eyes and ears and maybe, right? Whatever. Or you'll tell me, DJ, done. I don't want to repeat. Okay. So you got the point?
Yes, sir.
So therefore, the switch, when it knows that the source and destination both are on the same port, it will just drop it. And now presume that this MAC address was not in the MAC address table only. Now what? It has received it here. Now what will the switch do? Because it doesn't know where 4 is.
I'll just filter again.
No. Then it will forward from other ports.
Okay.
Isn't it? But anyway, it will never send it back from the same port. Isn't it? It's okay. You got the logic. Yes or no? Thanks. Dipti, I hope you can hear me. I lost you. Okay. Microphone shop.
Hello.
Okay, no
Hello.
problem. Yeah.
Yes, sir.
Yeah, okay. Sorry. I got a bit worried. I said, what happened? My voice is reaching or not? Okay. So now both the logics is clear, right? Logics are clear. Switch A sends a frame to B. The switch knows the MAC address for B. So it will do what? Both are on the same port, so it will drop it. Okay. ठीक है ना?
Yes, sir.
Good. So now, of course, if anybody sends a broadcast or a multicast, it will just flood it, right? So if D sends a broadcast or a multicast, it will receive on this port and just make Xerox copies and give it to everybody else. That's it. Okay. So Ethernet switches and bridges increase the available bandwidth of a network by creating dedicated network segments and interconnecting the segments. Look. Let's say they are 100 Mbps ports. So they run full duplex. So it can send and receive both the things at the simultaneously, right? So throughput goes up 100 Mbps, but 100 receive, 100 send. So throughput becomes 200 Mbps. Got it? Because we are presuming that they're operating on full duplex. This is one dedicated network segment. This is another dedicated network segment. So it is interconnecting the segments and also increasing the bandwidth of the network, right? Switches and bridges use one of the three operating modes to transmit frames: store and forward, cut through, and fragment free. Switches and bridges maintain a MAC address table to store address to port mappings, so it can determine the locations of connected devices. ठीक है? When a frame arrives with a known destination, obviously MAC address, it is forwarded only on the specific port connected to the destination. So we are done with chapters 12 also. They're all revision, guys. We have done switching. Let's go to chapter number 13. Redundant topology overview. Now we know what is a redundant topology. When you connect two switches with more than one cable, then we call it a redundant topology, right? So there are more than one ways of sending and receiving data. So upon completing this lesson, we'll be able to describe the features of redundant switch and bridge topologies, explain the problems associated with broadcast norms, multiple frame transmissions, and MAC address table instability. So if STP is disabled or if it's not born, and right, if we have if we have a redundant topology, then what will happen? All these problems will happen. Right? Broadcast norms will be created, or the destination will receive two copies of the same frame, right? Which of course the protocols don't like it. And the MAC address will also become unstable. I hope we have discussed all these things. Yes or no? This will happen only and only when STP is not enabled. Yeah. Describe loop avoidance and explain how it can solve redundant switch topology issues. So we know how STP works. Now we have a topology here. Redundant topology eliminates single point of failure. Okay, that's okay. So let's say, so the data is going like this. If this fails, it will start going like this, right? Redundant topology causes broadcast arms, multiple frame copies, and MAC addressable instability problems. That only if spanning tree protocol is not enabled or disabled, or it's not born only, right? So I hope you know we have discussed these things, right? Let me again try and recap. So what we are saying is, in case STP is not enabled, right? That means what? None of the ports are blocked. All of them in the forwarding mode. Right? And if this guy, let's say if it sends a DHCP broadcast, whatever broadcast, right? Then what will happen? It will receive the broadcast on this port because all ports are in VLAN 1 only. It will forward from this port. It will go like this to this guy, everybody, right? It will also go like this. It will come on this port. It will go to everybody else also. It will again, when it comes on this port, it will again go to this port again, right? Again. So again and 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 again. Also, when it had received here, it had sent from this port also, right? Again, it will come here. Again, it will go to everybody. Again, it will go like this. Again, it will go to this guy. Again, this guy. Again, it will come here. So it will never end. You get it? Again, it will keep on going to everybody else. So it will never end. So this is infinite loop. Now we are presuming STP is not enabled, or it's not born, or it's disabled, right? Infinite loop. It will never stop. All these devices will hang, right? Their CPUs won't be able to process so many, right, frames continuously, so they will hang. So network cannot work because none of these ports are blocked. All of them are in the forwarding mode. Got it? So what's happening? One is this is known as broadcast storm will be created. Secondly, multiple frame transmissions, right? Correct? A PC will receive multiple copies of the same frame. If the topology is like this, loop won't happen. PC1, PC2. MAC address A, 10.1.1.1. MAC address B, 10.1.1.2. If this guy pings this PC, this topology is not redundant, but if you connect it like this also, then what happens? Now the topology is redundant and STP is disabled, so none of the ports are blocked. All are in the forwarding mode. See that? What will happen? If this guy pings that PC, it will come here because switch 1 doesn't know. Of course, it will learn this A max on this port, that's okay. And it doesn't know where B is, so it will send a copy from here and one from there. So it will come on this, let's say switch A, switch B, switch C, switch D. It will come on switch B. He will note this A matters on this port, that's fine. It doesn't know B, so it will forward from here. This guy will receive here. It says, I don't know where B is, so he'll send one here, right? So he's got one copy. Okay, fine. Of course, it will send from here also like this. But now it sent from here also. It received A matters on this port, that's okay. It doesn't know B, so it will flood out from this port. It will be received on this port. It doesn't, it says, I don't know where B is. So it will send one more copy now to this guy. So look, multiple frame transmissions. One copy it received like this, and one copy it received like this. So unrecoverable damages. Protocols would like it, right? This is multiple frame. More than one copy is being received, right? Frame transmissions, right? So infinite loop, broadcast storms, multiple frame transmissions. These are the problems if the topology is redundant and STP is not. That means STP is not working means STP is disabled or not even born. So these are the problems that will arise, right? And MAC address table. So broadcast storms will be created, multiple frame transmission, and MAC address table will become unstable. That means incorrect. What does it mean? It means this. So one copy it received on this port. Let's say this is port number F0 oblique 10, right? Because, okay. So this switch D will note this MAC address in its MAC address table as what? A is equal to port number 10. And one more copy to receive from here on this port. Let's say this is port number F0 oblique 1. So now, got it? Problem? So now if this PC tomorrow wants to ping this guy, so if to receive on this port, and from which port do I send? Switch D. If I send from the first port, then also it goes to him. If I send from the 10th port, then also it can reach him. So from which port do I forward? Right? A switch cannot take action because one host should be visible from only one port, right? So now the switch cannot take action. So this is a big problem. So therefore, the MAC address table has become unstable, right? Incorrect. They call it instability. Instability problem. Got it? So when STP is enabled, let's say this port is blocked. Now it knows for sure, right? Right? Because from the block ports, it can never learn the MAC address. So only from one port, only from 10th port, right? So that is what STP helps us in, right? Where are we? So upon completing this lesson, we'll be able to describe the feature of redundant switch and bridge topologies, explain the problems associated with broadcast norms, multiple frame transmissions, and MAC address table instability. Describe loop avoidance and explain how it can solve redundant switch topology issues, right? So now we know STP how it works. Redundant topology eliminates single point of failure. That's okay, right? Redundant topology causes broadcast arms, multiple frame copies, and MAC address in case STP is disabled, right? Ignore this topology. Let's take our topology. You can take a topology like this, right? One PC here, one PC there. Or you can take four switches and connect them like this, whichever way. But make sure that topology is redundant and one PC here and one PC here. Okay. So STP should block one of the ports and leave only one path, right? Like this, whatever. So in that case, if this switch dies, or this path dies, or this path, it will bring this port in the forwarding mode and then communication will go happen like this, right? If STP is enabled. So we know how broadcast arms happen, right? Unending, they'll keep on sending. It will happen both ways, this way, right? As well as that way. Correct? Both ways. So I don't want to get into this topology, but if this sends a broadcast, it will forward from this port. This will forward from this port. This will forward from this port like this. And of course, it will keep going to other guys also, right? Switches continue to propagate broadcast traffic over and over again because STP is disabled. None of these ports are blocked, neither this, nor this, nor this, nor this. All in the forwarding mode. So therefore, right? And multiple frame copies, we have seen this, right? So in this example, ignore the topology. It says this server is sending router is receiving one from server like this and one more like this. So two copies, right? Okay. What more? I have told you about instability problem, right? That the four switches is good. First port or 10 port, right? Same things. So A and B incorrectly learn switches A and B to learn the macros. Okay, ignore this. I explained to you in the notepad, right? Switch networks are bridge and switch networks are commonly designed with redundant links and devices, which can introduce problems such as broadcast storms, multiple frame transmissions, and MAC database instability. A broadcast storm is when each switch on a redundant network floods broadcast frames endlessly, right? In a redundant topology, multiple copies of the same frame can arrive at the intended host, potentially causing problems with the receiving protocol. MAC database instability results when multiple copies of a frame arrive on different ports of a switch, right? Okay. So if you have any problems, do let me know tomorrow. Okay. So we are done with chapter number 13 also. So let's quickly move on to chapter number 14. Now this is spanning tree protocol. Now we have done this STP. Election of root bridge. Election of first is root bridge. The one which has got lower priority, or if priority is same, then lower MAC address. That will become the root bridge. Then election of root port. They are only on non-root bridges. Only one port, which will take you to the root bridge from the lowest cross path, right? And then election of designated port. And then all other ports block, right? This is how spanning tree protocol works. So upon completing this lesson, we'll be able to describe the purpose and operation of spanning tree. We know the purpose, loop avoidance. Explain how to implement STP to solve the problems associated with redundant switched or bridge topologies. Okay. So now we know what's going to happen. They are going to exchange BPDUs, hello, 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 every 2 seconds. This way, that way. This way, as well as that way. Right? From the block port also, BPDUs are sent and received, but it does not learn the MAC address. So STP, so it will block one of the ports, right? So if I draw it like this, maybe it will block one of the ports. So communication will happen like this only. Topology, you can draw it whichever way. So STP provides a loop-free redundant network topology by placing certain ports in the blocking state. And we know if this cable is removed, it will bring back this port in the forwarding mode, and then communication will happen like this. Okay. So how does it work? First is election of a root bridge. Only one root bridge per network. You may have n number of switches in your LAN, but only one switch will be elected as the root bridge. The one who has got lowest priority or lowest MAC address. All others will become non-root bridges, right? So only one root bridge, all other will be non-root bridges. Only one root port per non-root bridge. So 100 Mbps, 10 Mbps, zero cost, zero cost. 100 cost, 19 cost. So which is lower cost? This one. So this will be the root port. Election of root bridge, lower priority or lower MAC address. This is election of root port. This port becomes the root port. Election of designated port. On a cable segment between two switches, one of the port has to be a DP. Because this one is already a root port, this one will be the DP. Between these two, what's your priority? What's my priority? Both are same. What's your MAC address? What's my MAC address? Oh, who's lower? You are lower. So you become the DP forwarding mode, and I will block this port. Okay. Nowadays, it will be known as alternate port. Of course, in discarding mode, instead of blocking mode, they call it discarding mode. Instead of non-designated port, in RSTP, they call it alternate port. And all other ports are blocked. How the root bridge is elected? Because BPDUs are sent every 2 seconds. Hello, 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 hello. What are the messages that they are exchanging in the BPDUs? What's my priority? What's my MAC address? What's my priority? What's my MAC address? How many of my ports are in which VLANs? How many of your ports are in which VLANs? Right? Plus many more things. So BPDUs, bridge protocol with the lowest bridge ID. So priority and MAC address is known as BID, bridge ID. So bridge ID is bridge priority, which is 32,768 plus the MAC address, right? So in this example, which has the lowest bridge ID? Obviously, X has got a lowest bridge ID, so it will become the root bridge. None of the ports will be blocked on the root bridge. They will be known as DP. They'll all be in the forwarding mode. Correct? Now, we have seen all these things. Spanning the port states, blocking mode to listening mode to learning mode to forwarding mode. Therefore, when we connect a PC, it remains amber for 30 seconds, right? Remember that show span tree, listening mode, learning mode, and then forwarding mode. So blocking to listening mode is known as max age timer, 20 seconds. Listening mode to learning mode is known as forward delay, 15 seconds. Learning mode to forwarding mode is known as again forward delay, 15 seconds. Total convergence time up to 50 seconds. Very slow. STP, old one. Okay. Transits each port through several different states. In RSTP, it will be from discarding mode, there is no listening mode, to learning mode, and to forwarding mode. Right? Only 3 modes. Okay. So now this is becomes a DP. This one becomes a DP. This becomes a blocking mode, non-designated port, and this becomes a root port. Okay. Port states. Listening and learning are temporary, right? Or learning is temporary. End of the day, after convergence happens, a port has to come into forwarding mode or It has to go in the blocking mode. So now this is the inbuilt table that the switch uses to decide which port should I block, which port should I treat as root port or designate port or all those things, right? So look here, 10 Mbps, speed is going up, link speed, 100 Mbps, 1 gig, 10 gig. And this is the old standard, this is the new standard, right? Very, very old. Here, gig and gigabit, 1 gig and 10 gig were same. So 10 gig was not born, so ignore this. Let's talk of this one. 100 Mbps, 10 Mbps, cost is cost, just some value, right? 100, then 19, then 4, and then 2. So faster speed is good. But today it will be like this. Something like this. 2 lakhs and maybe 20 lakhs. So whichever, this could be the latest one, right? Cost. Anyway, the funda is slower link, more cost. High speed, low cost, right? Whichever table you want to consider. So now in this table, this topology diagram, we have 3 switches: switch Z, switch X, and switch Y. Look, everybody's priority is same. 30,768. Now who has got the lowest MAC address? This guy has got this MAC address. This guy has got this. This guy has got this one. So I think the lowest is this one. So this will become the root bridge, right? And let's say they are connected like this only. Okay. So this will send 0 cost, 0 cost. But 19 cost, let's say all of them are 100 Mbps. Let's say all of them are 100 Mbps. 0 cost, but 19 cost. 0 cost, but 19 cost. Okay. So this will be the root port. This will be the root port. DP we know. Root bridge, root port, root port. Between the two, one has to be DP. One has to be DP, root bridge, non-root bridges. Okay, you go in how much cost? 19. You go in how much cost? 19. So between us, what's your priority? My priority is same. What's your max? You're lower. So you become DP and I'll block my port. This one, blocked. Same things, correct? And now, supposing they were connected like this, supposing if this switch dies, the new root bridge will become this one, correct? New root bridge, because we are presuming everybody's priority was same, but this guy's magnitude was A, this guy was B, and this guy was C. So he will become the new root bridge, right? And because this is gone, so these ports are not going to remain up and up, they'll be up and down, whatever, down and down. And now this guy's root port, earlier it was this one, now this will become the root port, new root port, right? Again DP. What if this switch didn't die? What if the switch didn't die? Only this cable somebody removed it. So now the new root port won't be this one. The new root port will become this one. Because from here only it goes in 1919. This is still the root bridge. This is still the root port. This guy's root port is no more this one because it is no more up and up. New root port, right? So all these changes will take place automatically, right? We don't have to do anything. Is it okay, everybody? Now RSTP does the same things, but it does it very fast, right? It's based on STP only. There in RSTP also you have root bridges, right? And between the two switches, they call it point-to-point link type, right? We don't have hubs today. Edge types. So these are edge types, right? Okay. So these only some terms here. Okay. STP, okay, so we are done with STP, right? Is a bridge-to-bridge protocol used to maintain a loop-free network. We'll finish here. STP establishes a root bridge, and all others become non-root bridges. On every non-root bridge, there's only only one root port. And on the root bridge, all the ports are designated ports, right? So on and so forth. With STP, the root bridge has the lowest bridge ID, which is made up of the bridge's priority and MAC address. With STP, ports transition through four states: blocking, listening, learning, and forwarding. If a change occurs to the network topology, STP maintains connectivity by transitioning some of the ports to the forwarding mode and vice versa, right? RSTP significantly speeds up the recalculation of the spanning tree when the network topology changes, right? So RSTP is based on STP only, just that it's faster. So we are done with chapter 14, guys, right? 14th is done. So tomorrow we'll take up switching. 15th and 16th and 17th, and then we are done with switching. It's one day, right? And then we'll again jump into routing, the new topic. So I just wanted to cover up all the PPTs, which we have been quickly able to do it in a day or two. Okay, or three, whatever. Okay, guys, thank you so much. Good night. Have a nice time. See you tomorrow.